Hi there! Today we are looking at rendering a skybox with a Vulkan cube map. Here we are looking at a cube map. It has 6 faces, left and right, top and bottom, and front and back. Each of the faces is a quad. Each quad has 2 triangles, each with 3 vertices. So per face we have 6 vertices, and for the entire cube we have 36 vertices. At the moment we can render a cube already based on a shader using a 2D sampler and UV coordinates for the 12 triangles of the cube. Today we are looking at a different method of rendering a cube based on Vulkan features specifically provided for cube maps. The image view object in Vulkan supports a cube type directly, and in the fragment shader we can use a cube sampler that takes in UVW coordinates instead of the UVs that we're normally using. So it's a bit redundant what we're doing today, but using cube maps will be a fun exercise. We'll use this opportunity to review all engine functions again that are required to draw a texture and provide any information that fell short in the previous video about adding textures. Let's see how the skybox looks in our engine. This is Lucre, my example application. This is the main scene. Here we have a settings screen. And here we can switch over to the second scene. This is a cutscene. And there we go. So there's the skybox. Very beautiful. This scene is just brand new. It's still work in progress. It's going to be a side scroller. Yeah, and this is what we're going to implement today. To render a skybox, we need 6 equally sized quadratic images for the faces of a cube. A Cubemap class to load the image data, to create a Vulkan image and a Vulkan image view, as well as a sampler, a vertex and a fragment shader, a render pipeline that's using those shaders, a render system that creates the pipeline and that can issue draw calls. Then we need 2 descriptors for the fragment and vertex shader, one for the global uniform buffer with the view and projection matrix, and 1 descriptor for the cube sampler in the fragment shader. For the 2 descriptors, we also need a descriptor set layout. The descriptor set layout is used when we create the pipeline. A descriptor set layout is basically a type definition of a structure and is used during the pipeline creation for reserving the appropriate memory. Then we need a model that provides the vertices and a game object ID from our entity component system. Then we need to define a Cubemap component that can be used to loop over all Cubemap game objects in our entity component system. And finally, we need a scene to use the Cubemap as a skybox. I implemented the skybox already in my engine, and now I'm going to revert the Git repository to before I started working on this feature so that we can look at all the differences that I applied. We're going to start with the Cubemap class. In Engine Renderer, we have the files cubemap.h and cubemap.cpp. And in Engine Platform Vulkan, we have vkcubemap.h and vkcubemap.cpp. So in Engine Renderer cubemap.h, we have a generic definition of a cube map that's independent of Vulkan. So this interface has pure virtual functions only, except for one static create function that's implemented in cubemap.cpp and which has a switch, and depending on the switch it returns a shared pointer to the actual implementation. So in our case, a VK Cubemap. Then in engine platform Vulkan, we have vk-cubemap.h, and this is the implementation of the Cubemap class. So here we see the same functions, only that they are now overriding. And on top of that, we have some private functions that are Vulkan specific. All this here is very similar to the texture class that we discussed last time. Let's see how the implementation looks like. Here in the constructor, we're initializing everything to 0, except for nearest filter, which we're setting to this argument, and except for MIP levels, which we're setting to 1. MIP levels will stay 1 the entire time. I decided not to use it because we're using the Cubemap as a skybox, so it's always at the far end of the view frustum, and it will have the same MIP level anyway. In the destructor, we're destroying the Vulkan image, the Vulkan image view, and the sampler, and we're freeing the memory. Then in the init function, we're taking in 6 file names for our 6 faces, a boolean sRGB for the image file format, and a boolean to flip the images. Then here, we are looping over our 6 file names. Number of Cubemap images is defined at 6. In the Cubemap class, mLocalBuffer is an array of unsigned chart pointers with 6 elements. Here we are loading the file and we're initializing width and height and bytes per pixel. And here we are checking if everything went well. So if that was the case, we're calling create. And after that, we are freeing the local buffers. Now let's take a look at the create function. In the create function, we're calculating a layer size to width times height times the bytes per pixel. And then we're calculating an image size to the layer size times 6. As I explained before, the Vulkan image is not aware of the cube feature. It's just an array of multiple layers. Then we're creating a staging buffer on the GPU that can be mapped into CPU memory. Here we are calling create buffer with the image size. Then we need to map the staging buffer into the CPU memory with vk-map memory, which is returning a pointer to the staging buffer memory. Then we need to loop over our 6 local buffers and copy each buffer onto the GPU. So to do that, we have this memory address here that we calculate from the address of the staging buffer plus an offset. Once we have the data on the GPU, we can unmap the staging buffer. Then we're setting the format here. So depending on this parameter sRGB, we're setting it either to sRGB or to unorm. And unorm here is used for image files that do not contain pictures, that just contain our map data, for example, normal maps. So here we are calling create image, and with our format. Then the usage is transfer destination or sampled. Transfer destination, so currently we still have the data in the staging buffer, so we still need to transfer the data into the heart of the GPU. And sampled is because we want to use the image in the fragment shader and we want to sample it there. The memory property device will be local. So that is the most efficient for an image that just resides in the heart of the GPU. Then we need to transition the image layout. At the moment, it's still undefined, and since we're going to transfer it into the heart of the GPU, we're using transfer destination. Then we're calling this core function here, copy buffer to image, with the source is the staging buffer, the destination is our Cubemap image, we're passing the width and the height, and we also need to pass a layer count. So we need to set this value also to 6. Once we have copied the data into the heart of the GPU, we can transition it to its final layout, which is shader read only optimal, so that we can read it in the fragment shader. Then we can dispose of the staging buffer, we can destroy it or free its memory. Then we need to create a sampler. This code here is exactly the same as in the texture class. We're using here this parameter nearest filter. For normal pictures we want to use linear, and for pixel art we want to use nearest. Here we are calling VK create sampler. So then finally we need to create the image view. So this is where the cube feature comes in for the first time. We're setting the view type here to image view type cube. Then we're using the same format. We're using the same components that we use in the texture class. And what's different is that for view.subresourcesrange.layerCount, now we need to set this to 6. And yeah, that's it. Here we are calling VK create image view. And that's our Cubemap class. Then we need 2 new shaders, a vertex shader and a fragment shader. In the vertex shader, we're taking in vec3 for the position from a vertex buffer, and we're outputting UVWs also as a vec3. Here we have some boilerplate. This is my usual point light structure, which is required down here. In my usual global uniform buffer, that is holding the projection matrix and the view matrix. And we have push constants here that are holding the model matrix and the normal matrix. Then in the main function, we're calculating the model view projection matrix and multiplying it with the position. Here we're outputting the UVWs. This code down here is to flip the y-axis. The vertex shader is going to be called 36 times per frame for our 36 vertices. Then in the fragment shader, we're taking in the UVWs and we're outputting a vec4 with our color. So here is our new sampler, the cube sampler. Then we have the same boilerplate that we looked at before. And in the main function, all we do is we use the Cubemap sampler to sample a texture. So the vertex shader and the fragment shader are quite easy to understand. What's noteworthy is we have here 2 bindings, set 0 binding 0 for the global uniform buffer. So we will need a descriptor and a descriptor set for this. And here we have in descriptor set 1, bound at location 0, our new sampler. And one more thing. Normally in a Skybox implementation, the model matrix is not used. So you would see something like this, where the model matrix is assumed to be an identity matrix, and from the camera matrix or from the view matrix we are stripping off the translation component. If you remember, to scale and rotate an object we need a 3x3 matrix, and we extended it to a 4x4 matrix so that we can also fit the translation in the last column. So this is removed here so that the camera is always in the center of the cube. Well, I decided to go with this solution and to use a model matrix so that I can rotate it in my side-scrolling scene. Then we have a new render system called VK Cubemap Render System. The header is familiar to us from the tutorial series. We're creating here a structure for the push constants. We have a constructor that takes in a render pass and a standard vector of descriptor set layouts. We have a function called render entities that takes in our frame infrastructure and the registry of our current scene from the ECS. And it has two private functions: create pipeline layout, which also takes in a standard vector of descriptor set layouts, and a function to create the pipeline, which takes in a render pass. In the implementation of the cube render system, in the constructor we are calling create pipeline layout and create pipeline. In the destructor we are destroying the pipeline layout. Then the create pipeline layout function is the same as before. Here we're taking in the two descriptor set layouts that we discussed before. So we have one descriptor set layout that's holding our global uniform buffer, and a second descriptor set layout that holds the sampler for our cube map. In the create pipeline function, there aren't that many changes either, except for these two lines. So here we're setting pipeline config.subpass to subpass transparency. To explain this, per frame my engine is using two render passes, the first one for 3D and the second one for 2D. The 3D render pass is divided into three subpasses: geometry, lighting, and transparency. Geometry and lighting are used for deferred shading, and transparency is a forward rendering approach to render transparency, and in this case also our Skybox. The transparency pass still has access to the depth buffer of the first subpass, the geometry subpass, so if anything is in front of our Skybox, the fragment shader would not be called. And then in this line, we're setting the cull mode to cull mode front, because we're seeing the cube from the inside. So we will only ever see the back faces. That means we might as well just cull the front faces. Here we're adding our two new shaders to the pipeline. And then finally down here we have the render entities function that is binding the pipeline here. Then it retrieves from the registry a view to all game objects that hold a mesh component, a transfer component, and a Cubemap component. Then it's looping over those game objects, and for every game object it retrieves the transform, sets up the push constants, and is using vk command push constants to copy the push constant data directly into the command buffer. And finally, it's retrieving a mesh component, and if the mesh is enabled, it will here bind the vertex buffer and then issue a draw call. We will take a look at the draw Cubemap function in a little bit. For our model class, we also have 4 files. In Engine Renderer, we have model.h and model.cpp. And in Engine Platform Vulkan, we have vkmodel.h and vkmodel.cpp. In model.h, we're adding a new structure, primitive Cubemap, that's holding the first vertex, a vertex count, and a Cubemap material. Then in the builder class, we have a new function that's called load Cubemap, which takes in a standard vector of strings for the file names of our 6 faces, or 6 images, and the registry of the current scene. And the builder has also a standard vector of Cubemap shared pointers and a standard vector of Cubemap primitives. And in the actual model function, we have a new standard vector of Cubemap shared pointers called mCubemaps. In model.cpp, we have the implementation of load Cubemap of the builder class. Here, we're creating the vertices, we're creating a Cubemap, we're creating a descriptor set, and we're creating a game object. We're setting the vertex count to 36. Then we clear the standard vectors for vertices, indices, and Cubemaps. Here we are setting up the 36 positions for our vertices. And then for each vertex, we're only using the position. Everything else will remain 0. Then when we create the Cubemap, we call the create function we looked at before. We call init with our 6 file names and sRGB. To create the descriptor set, we're creating a Cubemap primitive where we set the first vertex to 0 and the vertex count to 36. Then we are calling the vk model to create a descriptor set with a material, with a Cubemap material, and the first cube map in our standard vector of cube maps, and we're pushing back the Cubemap primitive. And finally, to create the game object, we're loading the model into the engine. We are creating a new entity and a new mesh component initialized with the name Cubemap and the model that we just created. We emplace this component into the registry, and then we're creating an empty transform component and an empty Cubemap component that we're also emplacing into the registry. In vkmodel.h, we're defining the draw Cubemap function. We're adding a new function, create descriptor sets, that takes in a Cubemap material and a shared pointer to a Cubemap. And we're adding a standard vector for Cubemap primitives. In vkmodel.cpp, in the constructor of vkmodel, we're copying over the standard vector of cubemaps into mcubemaps, and we're doing the same for the standard vector of the primitive, Cubemap primitives. Then we have the draw Cubemap function. This is our draw call, which takes in our usual frame info structure and the pipeline layout. Then for each Cubemap primitive, we're generating a local descriptor set based on the descriptor set from the frame index of the cube material. Then we create a standard vector of descriptor sets that's holding our global descriptor set and the local descriptor set. Then we bind the descriptor sets to our pipeline. Here we pass in the pipeline layout. We pass in the number of descriptor sets to and the data. And then finally here we have the draw call, where we state the vertex count and the first vertex. And last but not least, we have the function create descriptor sets. This function is creating a local descriptor set layout. It's adding a combined image sampler for all graphics stages. And then it's creating a VK descriptor image info. And this function here is the connecting link to our Cubemap class. So this is where the sampler and the image view and also an image layout goes in, and these are the sampler and image views we created before. So this is how from the Cubemap class it gets into a descriptor set, and then we saw in the fragment shader that we were binding this descriptor for a certain set and for a certain binding, and so this is how all this works together. So this is how we get our data from the Cubemap class into the fragment shader. Image layout was shader read-only optimal. So the final layout from our Cubemap class. And then we're calling the VK descriptor writer for max frames in flight from the swap chain. So for each frame in flight, we will have to create one descriptor set. All right, just a few more changes to look at on the engine side. In components.h, we're adding a Cubemap component that we're using to loop over all cubemaps. In material.h, we're adding a Cubemap material with an array of descriptor sets with max frame in flight elements. Then in VK renderer, we are creating a Cubemap descriptor set layout, to which we're adding a combined image sampler that can be used in all shader stages in the graphics pipeline. Then we're creating a standard vector of descriptor set layouts, where we add the global descriptor set and the Cubemap descriptor set. Then we're creating the render system. And in our transparency path function, we're calling the render entities function of our Cubemap render system. And finally, we're adding the Skybox shaders to our list of shader files to be compiled. The application side is super easy. In our example scene in the header file, we're adding a new game object. In the CPP file, in the load models function, we're setting up the 6 file names. We're creating a builder, we're loading the Cubemap, and we're scaling it. And then in the onUpdate function, I'm adding a call to the transparency path. And that's rendering a Skybox in Vulkan with Cubemaps. Please leave a like on the video, and if you can, also on my engine on GitHub. Thanks a lot, and see you next time.